Good morning, everyone. Wow, we are packed. There's two seats, there's one there, there's two here, there's one there. We are packed. You know, last time we were consistently packed like this, I said, all right, I'm going to do 2 classes. And then no one showed up. We went down to 5 people, so I canceled the second class. All right, let's see. We have more people than I have these. I have 2 left, so we're gonna have to start sharing.
Here, we can borrow one.
Okay, there's one there. You guys can share. Who else? You need one, or you two want to share? Okay, and then I'll have one in case we have got a seat right there. And then why don't you guys share, just in case I have somebody that's sitting over there, I can hand this one to them. All right, good morning. Okay, we're talking about aircraft performance today. I've got a seat. There's one here if you'd like, Lucy. You good there? Okay, you're gonna need that.
Thank you very much.
Mm-hmm. Okay. Who read the chapter? All right. Not many. 1. 2? Oh, 2. Okay. All right. So again, I'll reiterate this, guys. If you will read these chapters before the class, and then also if you're part of Gold Seal, if you'll go through the Gold Seal stuff before class, okay? What I talk about is going to make a lot more sense to you, okay, if you have some background knowledge. All right, for those of you who read it, do you have any questions on what you studied so that I can write them on the board so that I make sure I cover them? Any questions in particular? All right. Okay, aircraft performance. Open up that binder, those little folders I gave you, and the first thing in there is a chart that looks like this. I want to just look at that chart first. So when I talk about aircraft performance, just like when I talk about aerodynamics and many other subjects that I do in this class. In fact, out of the 14 classes, this chart does or could come up in 9 of them, okay? Because this is this is a chart of the standard atmosphere. And so where are we flying when we fly an airplane? Where are we doing that at? Where's that occurring at? It's occurring in the atmosphere. And the atmospheric conditions affect greatly what happens to the airplane and how it performs. All right. So I want to just do a review of this. I know you've seen it before, but I just want to do a quick review of this. So this top line right here, this top line is the standard atmosphere, right? And this is basically the line that I said as a pilot, everybody in this room needs to know. All right. So standard atmospheric pressure in inches of mercury is what at sea level? 29.92 inches of mercury, right? Standard temperature, here it's only given to us in Fahrenheit, but what is it in Celsius? 15 degrees Celsius, okay? All right, so the standard pressure, standard temperature, you don't really need to worry too much about this stuff right now. I might talk about it later, but right here, these 2 columns, pressure and temperature. And then what happens, and I should probably add a Celsius temperature here, but what happens as we go up every 1,000 feet in mercury, about an inch, approximately 1 inch of drop, and temperature Fahrenheit's 3.5 degrees, but Celsius is what? 2 degrees Celsius. Okay, so we want to remember that as we go up in the atmosphere, the pressures, the density of the air decreases, right? Because we don't have as much atmosphere above us, so there's not as much weight. There's not as much the atmosphere. The air is not being compressed as much. Molecules are spreading out. All right, so as we go up and the molecules spread out, the air gets thinner. The way the aircraft performs changes. As the temperature of the air increases, that also causes air to expand. It also causes the molecules to expand. So high temperatures are similar to high altitude. So high temperatures could cause the density of the air to expand as such that we're at a higher altitude. Okay? Everybody got that? All right. So everything that we're going to do today, we need to really think about the atmosphere and how the atmosphere, what it does to us. All right, so the first concept, and this is not new, hopefully, to most of you, that I want to talk about is pressure altitude. Pressure altitude. When we were talking about instruments and we were talking about altimeters, I think we did that last week, right, or the week before. One of the weeks. Last week was weight and balance. So the week before we talked about instruments, and one of the instruments was the altimeter. Okay, and we said the altimeter is a pressure instrument, and we went over all the different types of altitude: true altitude, absolute altitude, pressure altitude, and density altitude. Right. So pressure altitude is that altitude we talked about, that is the height above the standard datum plane. So what is the standard datum plane? Okay, is it sea level? Is the standard datum plane sea level? Katie, is the standard datum plane sea level? No. That might be. It's wherever 29.92 exists in the atmosphere. It might be sea level. It's sea level on a standard day. Okay, but it's not always sea level. So it's wherever that happens to occur. All right, so it's a theoretical level where the pressure is 29.92. And here I've got and temperature's 15 C, but and that's really what it would need to. That's what the standard atmosphere would be. But where 29.92 exists, the temperature may not be 15 C. That's still the standard datum plane. So this actually is kind of not correct. There's two methods of finding the standard pressure, or excuse me, the pressure altitude. One, as we talked about during instruments, is you take your instrument, you set it to 29, your altimeter, and you put 29.92 in the Colesman window, and you read it. So if 29.92 is set in the altimeter, and you read what the altimeter indicates, you are reading pressure altitude. That's an easy way to do it. The other way to do it is this mathematical formula right here, which is pretty simple. Because we understand as pilots that pressure changes by 1 inch per 1,000 feet, or approximately 1 inch per 1,000 feet, we can use the fact that if we take 29.92 minus the current altimeter setting, whatever that is, multiply it by 1,000, we're going to get the difference in altitude, plus or minus, in feet, the difference in altitude between the current and standard, and then if we add back our indicated altitude, we have our pressure altitude. So that's another way of getting pressure altitude. All right, those are the two ways. Set your altimeter to 29.92, or take your standard pressure of 29.92, subtract whatever the sea level pressure is that day, multiply that times 1,000. So let's do that. What's the pressure right here? I'll show you an example of that. So we're going to take 29.92, okay, minus, somebody look up the ATIS, tell me what the altimeter setting is right now. We're going to calculate the pressure altitude right here at this field right now. You looking that up? Okay.
Saying it's 30.05.
30.05.
Right here it is.
Yep, 30.05. Okay, so as long as you got your phone out, do the math on that for me. 29.92 minus 30.05. Negative 0.13 times 1,000 would equal 130 feet. Is that right?
Yes.
It'd be a negative 130 feet though. Negative 130 feet plus the field elevation is, let's call it 650, equals what? 650 minus 130 is what? 520 feet. That's the pressure altitude right now. 520 feet. So if we were to go out to the airplane and put 29.92 in the altimeter, it would read 520 feet. So we could go to the altimeter and do it, or we could just do the math. If you're at home, let's say you're planning something and you want to know what the pressure altitude is, you can do the math, come up with it. All right, those are the two methods of finding pressure altitude. All right, I'm going to skip through a couple of slides here. I want to get to density altitude. This is the holy grail of altitudes. Let me put the altitudes up here. We have true altitude. We have absolute altitude. we have pressure, altitude, and we have density, altitude. So just a quick review. True altitude is what? What is true altitude? Height above what? Height above sea level. Remember, altitudes are always measuring, when we say an altitude, we're saying some height above something, right? It's the question of what is it above, right? True altitude is above sea level. Absolute altitude is height above ground level. Pressure altitude is height above the standard datum plane. So wherever 2992 exists, that's where pressure altitude is, okay? And density altitude, this one's a little different. Density altitude is a theoretical height, if you will, of where the airplane thinks it's at based on atmospheric conditions. So that's the one that really, when we talk about performance, that is the most important altitude that we have to really understand, okay? And it's not a true altitude in which you could take a tape measure and measure down to something. All right, if we're in the airplane and we're flying at, let's say we're just flying and we take a tape measure that's long enough and we take it all the way down to the ocean and we read it and it says 1,000 feet, then our true altitude is 1,000 feet. If we run it down to the ground, wherever that's at, and it says 700 feet, then our absolute altitude is 700 feet. If we run it down to wherever the pressure is 29.92 and we read it, and it says 520 feet, then our pressure altitude is 520 feet, okay? But our density altitude isn't something we can actually take the tape measure down and stop here and measure up. Density altitude is pressure altitude corrected for two things: non-standard pressure and non-standard temperature. So we have to put a correction factor on our pressure altitude in this case to figure out what the density altitude is. All right? So there's a couple of ways to do that. One is to use a chart that looks like this. And one is to use your E6B. Who's got their E6Bs with them today? Okay, good. Pull your E6B out, because we're going to do that in just a second. Let's look at this chart right here, and let's figure out what the density altitude is here at this airport. It's a kind of a cool morning, so it's not going to be too bad. Temperature is going to affect it, but so what is the temperature right here in Celsius right now at this airport? So we know this is our pressure altitude right here. What's the temperature? Yeah, right here. 70. What is it in Celsius? Well, here. Here we can use this. 75. Temperature 75. So right here. So temperature 75 right there. And if we go up to a pressure altitude of 520 feet, so this would be sea level right here. So 500 would be right here. So maybe right in here somewhere. And then we were to go straight across. Our density altitude is somewhere around 2,000 feet. Okay, look up the ATIS again. It'll tell you the density altitude here at the airport right now. What does it say? It's going to be around 2,000 feet.
1,800.
1825. Okay. So what does this mean? I'm just going to use 2,000 as an example here. What does this mean? What it means is that today, right now, at this very moment, if we go get in the airplane and we go to take off, the runway distance that we need to take off is going to be as if we were at 2,000 feet or 1,875 feet on a standard day. So if it were a standard day and we were 2,000 feet above sea level, that's how the aircraft's going to perform. That's how much runway we're going to need to take off. How high above sea level are we right now? We're 650 feet above sea level. But it's not a standard day. How often do we have standard day in the atmosphere? Like never. It never happens. You might have standard pressure at sea level, but do you have standard pressure plus standard temperature, and do they both lapse exactly the way they need to lapse as we go up in the atmosphere? And the answer is no. It doesn't happen. So we're always having to make some adjustment. This is why we have to understand the standard atmosphere. We have to understand that temperature and pressure on a standard day are 2992 at sea level and 15 degrees Celsius. That's the standard. And as we go up every 1,000 feet, the pressure changes by 1 inch and the temperature changes by 2 degrees Celsius. That's our baseline. And from that baseline, we make adjustments to calculate density, altitude, and also true airspeed, which is another thing we'll be talking about today. All right. Kind of sort of clear? A little bit? Getting there? All right. What can I do to help you get there? Okay. All right. All right. So that's one way to do density altitude, or density altitude by using a chart like this, and you just simply come up and look here. Here's our standard temperature. So if we had standard temperature at 520 feet, we'd be at 520 feet. If it was standard pressure and temperature, then, or excuse me, let's say at 650 feet. Let's say we were actually at 650 feet. Standard pressure and temperature, everything lines up. Does that make sense? All right, but we're not standard. Nothing is standard. All right, get your E6B out if you have it. And the way you use an E6B, here you go, is when you, and we have an entire class on E6B, so I'm not going to spend a lot of time doing this. I'm just going to show you real quick. If you have it, when you have it in the neutral position like this, where all of your numbers are lining up, you have two windows over here. And you'll see one of them says density altitude right there, okay? What you'd need to do is set the pressure right here in thousands of feet opposite the temperature right there, and then just simply read it, okay? Now, I have this, this is right now, it's set to sea level at 15 degrees Celsius. So sea level right here at 0 is at 15 degrees Celsius. So that's kind of the standard setup. This next slide, I'm using an example here of a pressure altitude of 3,000 and a temperature of 38 degrees Celsius. So if that were the case, if your pressure altitude was 3,000 and your temperature is 38 degrees Celsius, here's so these are in thousands of feet. So here's 1,000, 2,000, 3,000 feet right there. 10, 20, 38 degrees Celsius right there. In that case, the density altitude would be about 6,000 feet. Regardless of what your true altitude is, regardless of how high you actually are above sea level, the density altitude in this case, the airplane is going to perform in this case like it's at 6,000 feet, where the air is much thinner. So the density of the air is as if it's at 6,000 feet. That's why we call it density altitude. When we say density altitude, we're saying the density of the air right now where we are is as if we were at 6,000 feet. That's density altitude, okay? So when we do the class on the E6B, we're going to do a lot of problems with that. So those are the two methods of calculating density altitude. Often, very, very often, your AWOS, ASOS, and ATIS will give you a readout. They will tell you density altitude, whatever it is, okay? Okay. So these are the two basic methods. The effects of temperature on density altitude are what? As the temperature of the air increases, what happens to density altitude? As temperature goes up, what happens to density altitude? What do you think, based on what we just said? So the temperature expands. The temperature expands the air, so what happens to the density altitude? It goes up. As the temperature goes up, so does the density altitude, because the air is expanding, the molecules are getting farther apart. It's as if we were higher in the atmosphere, simply because of the higher temperatures, okay? All right, effects of pressure on density altitude. Well, that should be straightforward. If pressure decreases, what happens to the density altitude? Does it go up or down? It goes up. Yeah, because as we go up in atmosphere, pressure decreases. All right, humidity. We didn't talk about humidity. How does humidity affect density altitude? If we have a very humid parcel of air, what's that do to the density of the air?
It's going to make it more dense because it's holding water molecules.
It's going to make it more dense? Who agrees with that? It's going to make it less dense. It's going to make it less dense because the water molecules take up the space and they push the air molecules apart. right? Okay, so the more moisture in the air, the less. Now, it's kind of like, I liken it to this. Having lived in Chicago for 30 plus years, I liken it to this. It can be 30 degrees outside, but it can feel like -10. Okay, so what the moisture does to the air is different than what it feels like. So when it's really moist, it feels like, man, the air is thick and heavy, and I could cut it with a knife. But that's not the way. That's not what happens with the airplane. What happens with the airplane is the air molecules get spread apart, and so that causes a higher density altitude. Okay. Okay. Any questions on? I want to make sure everybody's got this down, because when we start moving into the performance charts and stuff, and by the way, the performance charts are all going to have two things in them that will automatically get us to density altitude when we start looking at the charts. And the charts will be laid out as if you've looked through the binders here that I handed out. You'll see that there's two ways that the manufacturers typically lay out their performance charts, either in a graph format or a table format. And regardless of whether it's a graph format or a table format, there's two things that you'll always see on them. What two things you think you're always going to see?
Say the question again.
If we're going to calculate performance, what's the one thing that dictates the performance of the airplane based on what we've been talking about so far? What's the one thing that dictates the performance of the airplane? Density altitude. That's the thing that dictates the performance of the altitude. What is the density of the air? If I say, how's the aircraft going to perform today? You have to say, well, what's the density of the air? That's the question. That is the question. What's the density of the air? Okay. So if I want to know the density of the air, I have to know two things. What are those two things? Pressure and temperature. So every single performance chart will have a pressure side. You know, look at your X and Y. Your X and Y. You can have pressure and temperature. You have to. If you don't have those two things, you don't have a performance chart, because performance has to take into account pressure and temperature. Understand that? All right. All right, let me go back to, I want to go back to just something real quick here. I want to go to this right here, and I want to put some things up here to, you've probably seen this before. I've used this before in the past. This pink line right here, in this case, we're gonna let that represent the standard datum plane. So what is the standard datum plane?
29.92.
That's where 29.92 exists. So this line right here on this chart, it represents the standard datum plane. So if we were, I kind of want to show these altitudes to you, at least with these three anyway. Let's say that we are right here in the atmosphere. We're flying along right there in the atmosphere. What's our true altitude? What's our true altitude? You yell it out.
Last down.
True altitude. 9,000 feet. True altitude. 9,000 feet. Okay. What's our absolute altitude? 9,000 feet. There's the ground. Okay. If we're over here, what's our true altitude?
2,000.
True altitude.
9,000.
What's our absolute altitude? 2,000 feet. Right. Okay. All right. All right. What is our, if we're right here, what's our true altitude?
9,000 feet.
What's our absolute altitude approximately? 8,700 or something, right? All right. What's our density altitude? Well, or excuse me, what's our pressure altitude? Pressure altitude is 9,000 feet. We're coming right through sea level. What if we're right here? We're right there.
8,000.
What's our pressure altitude? 8,000 feet. If we're right here, what's our pressure altitude? 7,000 feet. See the difference in the altitudes? Okay. So with these three altitudes, not with density altitude, but with these three altitudes, what we're doing is we're setting up the altimeter, or at least we're measuring a height above something. We're measuring a height above something, either the sea level, the ground level, or wherever the standard datum plane happens to be in the atmosphere. With density altitude, we are calculating a theoretical altitude that would exist on a standard day if pressure and temperature are this, or whatever it is. Or we're taking this line, the standard datum plane, and we're adjusting it for the difference from standard pressure and standard temperature and coming up with an altitude that the airplane thinks it's at. It's going to perform like it's here. Okay? Clear as mud? Questions? Okay.
You know, from a perceptual point of view, you know, especially with these light airplanes, you don't tell that much. You know,
What do you mean tell that? What do you mean?
well,
You mean from a performance standpoint?
From your personal perceptive viewpoint.
On performance you're talking
On
about.
performance,
Okay.
for the most part.
Well, these are pretty good. These have pretty good performance.
Right.
However, you're going to have you flown in the winter in the cold months?
I have not flown in cold months.
Okay, so you're going to notice a difference when you get into the colder air. How's the aircraft going to perform in colder air? A lot better. A lot better. Yeah. You will notice a difference. Even though these are
Climbing performance would be much better.
everything. Takeoff distance, climb rate. There's only one. So generally speaking, and I'll tell you right now, generally speaking, when we talk about performance, when I say performance, what am I referring to? When I say aircraft performance, what metrics am I measuring? Or what am I taking metrics off of? What am I trying to figure out? Runway length for takeoff, that's one I'm measuring. Not RPMs. No, you're taking at this RPM, what is the performance? But the performance that I'm measuring is how much runway length do I need? Okay, so let's take it through a normal flight. What's the first performance number I need to look at? Runway length, takeoff length. How much runway do I need? What's the next thing I'm going to look at? Climb rate. How fast am I going to climb? What's the next thing I'm going to look at? Cruise speed. How fast am I going to fly through the air? Okay. And then through all of this, I'm also looking at fuel burn. That's another thing I'm looking at, right? Okay. And then what's the next thing I'm going to look at? You could look at descent and then landing distance, right? So when we talk performance, that's what we're measuring. That's what we need to know. We need to know, how's the airplane going to perform? And we don't think about that with cars. What do we think about with cars from a performance standpoint? Gas. Gallons per hour. That's all or miles per gallon. That's all we think about with cars. With airplanes, we have to think about all of these things, because guess what? All of those numbers change every day. Every day it can be a different number. Every single day. Because the atmosphere is never the same. And it can change. The performance of the airplanes out here 10, 15 minutes ago when we came up with this, and we came up with a density altitude of 2,000 feet, at noon, it's going to be different. You're going to have different performance numbers at noon. By 5 o'clock this afternoon, different performance numbers. Aircraft's going to perform differently. So it's really important you understand when it comes to aircraft performance. We can get, what you're saying, Delbert, is we can kind of get lazy with these airplanes because they perform really good. They're really good performing airplanes. Okay?
Yeah, that's the idea of which
That's
we as students are trying to grasp.
Right. So that's why I really want to make sure you understand this. First of all, there's only 2 seats in that airplane, so we don't have a big weight envelope that we have to work with. All right, we don't have a big difference in a delta in weight. it has a lot of power for even at gross weight, okay? So even when you go to the extremes of the weather conditions, or let's say the density, altitude, atmospheric conditions, it's still, I like to say if the airport is charted on a chart, I can take off or land on it with that airplane. Pretty much any time, really. I mean, I still want to look at it, but I can pretty much get away with it. As soon as you move out of this kind of airplane, you get into something that has more seats and less power to weight ratio like these have. Now we start getting into some problems, all right? Now you can get yourself in a situation where you might be able to take off in the morning, but wait 2 hours and you won't make it off the runway. You see what I'm saying? So you need to really understand how important the atmospheric conditions are when it comes to how the airplane performs, because it can kill you and it kills people when they don't take this stuff into account. All right? Very important you understand the relationship that's going on. And the abilities and capabilities of the airplane that you're flying, as well as your capabilities to pilot the airplane. Really important that we understand those things. All right? Okay. Okay, so here's the things, the terms that we're using. This is what we're kind of measuring, generally speaking. So takeoff, landing distance, rate of climb, ceiling. Yeah, how high can we go with this thing? Another thing would be payload. How much can we carry in the airplane? Range. How far can we go? Speed, maneuverability, stability. We talked about last week, and then fuel economy. These are when we talk about the performance. How's the airplane perform? These are kind of things that we look at. When we're talking about generally kind of day to day, I want to get out of this airport today. It's takeoff, landing distance, rate of climb to clear things, range, you know, how far can we go before we have to stop for fuel, that kind of stuff. Okay? All right. So we'll look at these. We'll kind of start looking at these one at a time, and I'll start with straight and level flight. So what is level cruise speed, and how do we get it? It depends on the aerodynamic shape and the drag of the airplane. Speed, you might think, most people think, speed is related to power and thrust. Well, it's really not. It is, but it's not, okay? There's a tiny, tiny portion of it comes from power. A much bigger portion of it comes from the aerodynamic shape of the airplane. The aerodynamics, and the lower the drag, the more speed you're going to get with a given amount of power. So that's primarily where this comes from. So you can think about that with a glider. A glider doesn't have an engine, right? But it has speed, and it can go faster or slower, right? Based on how much drag or induced drag or parasitic drag that we put on the airplane. Okay? What controls speed in an airplane?
No.
What controls speed in an airplane?
Your pitch.
What controls speed in an airplane? You change it with pitch, but that's not what's controlling it. What controls speed? You're onto the right thing, but it's not pitch. No. Who said angle of attack? Angle of attack. Angle of attack controls airspeed, not pitch. We change the angle of attack by changing the pitch, but it's not the pitch that controls the airspeed. Okay, this is another area people have a hard time, they get confused on. Let me just show you something real quick. Where's that stick? All right, so what's angle of attack?
The
Angle between what and what?
angle between the nose and the cord.
The chord line and the, not the pitch, relative wind. So let's say, and the relative wind is opposite and parallel to flight path. So let's say the top of this ruler here is the flight path. So Here's my flight path. That means the relative wind is that direction. Okay? Angle, the chord line is the imaginary line between the leading edge and the trailing edge of the wing. So if this is my flight path, and I have the airplane flying like this, let's say, and put it on this side, you can kind of visualize the angle of attack, right? Okay, that would be angle of attack. That'd be a high angle of attack. That'd be a lower angle of attack. Okay? If I were climbing like this, that would be a low angle of attack. Right? Because I'm going in that direction. If I'm going like that, that's a low angle of attack. So it's the angle between the direction of the airplane, the flight, or the opposite of the path, and this imaginary line. That's angle of attack. Pitch is the angle between the longitudinal axis of the airplane and the horizon. That's a low pitch. That's a high pitch. That's a negative pitch. So this is pitch, right? So I can hold the airplane here like this, and everybody in this room can say that's a high pitch. But nobody can tell me what the angle of attack is, because I need to show you the movement of the airplane to get the angle of attack. So in this case, this is a high pitch and a low angle of attack. This is a high pitch and a high angle of attack. So you have to have movement, right? Everybody understand that? All right, now, if I put this airplane back on here, and I just set it like that, and you see the angle of attack, right? So is that a high angle of attack? This is my flight path.
Yeah.
So you're seeing the movement here by the stick. Is that a high angle of attack?
Yeah.
Is that a high pitch?
So it is a,
Yeah, it's both. Both of them are high pitch, right? In this scenario, if I pull whatever power I have, if I reduce the power and I leave the airplane trimmed where it's at, here's what will happen. Is that a high angle of attack? Yes, didn't change. Did I change the pitch? Yes. So I can have a pitch change without an angle of attack change. So in all of these cases right here, my speed is the same. This is the same speed. Same indicated airspeed. Way different pitches. What controls airspeed? Pitch or angle of attack? Angle of attack. Angle of attack controls airspeed, not pitch. We can change the angle of attack with pitch. We can also change angle of attack with power and not change airspeed, right? So that's important to grasp that concept. Okay, so airspeed is a function of angle of attack. And the faster we want to go, the lower the angle of attack goes. And then our total speed with a given airplane and engine combination is going to really depend on, or our fastest speed in level flight is going to depend on drag, or the least amount of drag we can get, the faster we're going to go. Okay? All right, so that's straight and level flight. Climb performance. We talk climb performance. There's two kinds of climbs that we talk about. We talk about, well, first off, there's two factors that contribute to climb performance. One is excess power or thrust above that required to maintain level flight. This is typically how we climb an airplane. We use excess power or thrust, okay? There's another way, and that's by converting kinetic energy to altitude or potential energy. So if we're flying along, let's say we're doing 100 knots or 120 knots, and we just yank back real quick, what are we going to do? We're going to gain altitude, but it's a short-lived thing, right? We'll gain some potential, but as soon as we start doing that, what starts happening to our airspeed? It starts bleeding off, right? And at some point, if we hold it, we'll stall. So we can't hold it forever. We can gain whatever altitude we can gain, then we got to get that nose back over. So we can trade kinetic energy for potential energy, but just a little bit. We can't sustain that for very long. So that's typically not how we climb. I call that a zoom climb. So you could do that if you need to gain 100 feet or something. That's easy to do. What we generally do, though, is we use excess power or thrust to climb. So what controls airspeed? What controls altitude? Power. Power controls altitude. Okay, power. So we power for altitude, and then we say we pitch for airspeed. That's why you get confused when I ask people what controls airspeed. They always say pitch, because as instructors, here's what we say. We say pitch for airspeed, power for altitude, right? We say that because it rolls off the tongue. It's easier to say pitch for airspeed, power for altitude than it is to say angle of attack for airspeed, power for altitude. It just doesn't roll off the tongue as well. But that's really what's happening, is we're changing angle of attack, okay? All right, so we have two climbs that we deal with. We deal with a best rate of climb and a best angle of climb. These are the two types of climbs that we typically use, right? Everybody here familiar with that? Maybe a few people, if you haven't started training, you may not know what this is. Best angle of climb we call VX. VX is best angle. Best rate of climb we call VY. So let's talk about these two real quick here. Best angle of climb is a comparison of altitude over distance. So we want to gain the maximum altitude over a distance, i.e. a runway, a short runway or a runway length or something like that. So we want some gain, max gain of altitude over some defined distance. That's VX. VY is a comparison of altitude over time. So now we want maximum altitude over the next 5 minutes or the next 10 minutes or something. We want to gain the maximum altitude over time. Okay? X is angle, Y is rate. Okay. So up here I said excess power above that required to maintain level maintain level flight. So there's two things, and I unfortunately frequently use them interchangeably, but they're not really interchangeable. We have power and we have thrust, and those are two very different things. Power and thrust are two different things. Thrust is one of the four forces. Thrust is a force. Power is not a force. Power is a function of rate. Okay? Power is a measurement of how long it takes to move something some distance. That's power. Thrust is a force. So we use them kind of interchangeably, but I want to try to be careful not to do that in today, all right? So best angle of climb, okay, VX, best angle of climb, depends on excess thrust. Best rate of climb depends on excess power. Okay? And the way to remember that is, which one is VY? Best rate or best angle? Best rate. VY is best rate, and power is a rate thing. Therefore, VY requires excess power. VX requires excess thrust. Okay? That's the way to think. I'll show you these in a graph here in just a second, show you how the power curve and the thrust curve look on a graph and how it works. All right. When are we going to use best angle versus best rate? Well, best angle, we typically only use best angle when, for those of you that are flying. When do we take off and climb at best rate of climb? When are we going to do that? Clearing an obstacle. That's the only time. If we have an obstacle that we got to get over and it's a short distance away, there's a tree or a building off the end of the runway. I have to take off and get over that tree or that building. I don't want to hit it. Therefore, I'm thinking about gaining altitude as rapidly as I can over a distance. Therefore, I'm going to use sheer thrust getting up there like this. Okay? So I'm going to use VX. VX is always going to be a slower airspeed than VY, because you can imagine the angle of attack that's occurring. Hopefully you can imagine it. If for those of you that have not started flying yet, right? Have you started flying yet? Have you begun flying? Okay. If you have questions, stop me, okay? All right. VX is going to be a higher angle of attack than VY. Therefore, if VX is a higher angle of attack, the airspeed is going to be slower. It's going to be a slower airspeed. You can imagine the thrust. Imagine the thrust. If I point that thrust like this, I'm getting a little bump to get altitude. I'm using excess thrust to gain altitude over a short distance. Okay? So with VX, I'm going to use excess thrust, and I'm going to fly at a lower airspeed in order to get that propeller pitched up, get that thrust vector pointed that way a little bit more to get that altitude. Okay? VX is a dangerous place to be when you're close to the ground. And when are we typically flying at VX? When we're close to the ground, right? And it's a dangerous place to be because you're at a very low energy state. Your airspeed is very low. Your kinetic energy is very low. And what's your potential energy? Very low. You're low, low. Everything is low. And we're relying on what to keep us from coming out of the sky? Power, engine, thrust, right? So if the engine hiccups or quits, we're in a bad place, all right? So VX, I'm not saying that you should be scared of it, but I'm saying that you should be, you need to have a heightened awareness when you're doing a VX climb. You have to have a heightened awareness that this is not a place I want to be. I want to be here for as long as I need to be, and then I want to get out of it. So I'm going to clear my obstacle, and then what am I going to do? I'm going to get back to VY. I'm going to lower that nose and go back to VY, and then come back to a best rate of climb situation. If I have a short field, and I really need to get off the runway quickly, okay, am I going to climb at VX once I leave the runway? When would I climb at VX once I leave the runway? What if there's no obstacle? Then I wouldn't climb at VX. I would use short field technique to get off the ground, but there's no need to put myself into a dangerous VX climb. If I'm not worried about hitting anything, I'm just trying to clear corn. I'm not going to pitch the nose up there, right? So VX is used only when you have an obstacle or when you're practicing with your instructor or you're taking your check ride and you're doing a short field takeoff, because then there's an assumption that there is an obstacle and you're showing them that you know how to clear the obstacle. Okay? All right. So that's VX. VY, best rate of climb, is going to give us the maximum altitude gain over time. So if I want to climb to 5,000 feet and I want to do it as quickly as I can from a time standpoint, I'm going to take off and I'm going to hold a pitch attitude that results in an angle of attack that gives me the airspeed for VY, whatever that is. Any airspeed faster than that will take me longer to get to 5,000 feet. Any airspeed that I fly slower than that will take me longer to get, from a time standpoint, to get to 5,000 feet. So VY is a rate thing, so it's a time thing. Best rate of climb. So are we using excess thrust or excess power for best rate of climb? Excess power, because power is a rate. Power says, how much time does it take me to move 50 pounds 1 foot or whatever? I forget what a horsepower. Anybody remember what a horsepower is? 1 horsepower is how much time does it take to move this much weight 1 foot or something like that. That's what a horsepower, whatever it is. But the point is it's a time function. It's a time thing, rate. So anytime you hear rate, think clock. You hear rate, think power. Okay?
1 horsepower is the power it takes to move 550 pounds 1 foot in
1
1 second.
Okay, move 550 pounds 1 foot in 1 second. That's 1 horsepower. All right. Oh, let me go back here. Did I miss anything? Okay, let's look at these here. So climb performance killer. So weight. I've talked about this a lot. Weight is the enemy of an airplane. It is the enemy of an airplane. If you ever buy an airplane, the best thing you can do is lose weight. If you're overweight, like me, the best thing you can do is lose weight if you buy an airplane. Okay? Increased altitude or atmospheric conditions, density altitude. That's a killer. That's an aircraft. That's a performance killer. Increased drag, performance killer. So weight, drag, and high density altitudes. Okay, so if you're flying out of Denver on a standard day, is that a high density altitude? Would you consider that a high density? Absolutely, you're 5,000 feet up. Even though it's standard density, it's still high, right? So whether it's the actual, even if it's a standard day at 10,000 feet, it's a high density, right? Okay, so the atmospheric conditions are going to affect performance. The weight, higher weight degrades performance. More drag degrades performance. Okay, so just keep these things in mind. All right, let's look at the angle of climb. All right, so here is this is a thrust required curve. This is thrust or drag. Remember that aircraft in equilibrium, what are the four forces?
Thrust, drag, weight, and lift.
Okay, and what are the two that oppose each other in this direction? Thrust and drag. Therefore, they have to be in equilibrium, right? So if I draw a graph of thrust, it is also a graph of drag. They're the same line when they're in equilibrium, right? So in this example, what's showing here is if I'm flying at whatever this speed is right here, I'm generating this amount of thrust and that amount of drag. So if I'm generating 50 pounds of thrust, I'm generating 50 pounds of drag. So it's the same line, right? Then if we put the thrust available, in other words, how much thrust would be available at these speeds, okay? What you see is that back here, where we have the greatest difference between how much thrust I need to fly at this airspeed and how much thrust is available if I have the throttle full open at this airspeed, I have the greatest amount of difference. Therefore, I'm going to climb faster vertically than at any other airspeed from a VX standpoint. Okay? Do you see how that? So if I tried to clear an obstacle and not fly at this speed, but fly at this speed, I'd still climb, but I only have this much excess thrust to do it. So my rate of climb is going to be much less. I'm not going to gain as much altitude as quickly as if I do it at this speed where I have a bigger difference in thrust available. Okay? Make sense? Kinda? Everybody's shaking their heads, yes, but I don't know that I believe everybody. But, okay. All right, so there's angle. And angle is excess thrust. Excess thrust. Okay? And then here's power, or here's Vy, here's rate. So here is power required. Now, it looks kind of like the same curve. It's not exactly the same curve. It's not exactly the same curve because power and thrust are two different things. You can mathematically calculate and get those curves, calculate those curves, but you're not exactly the same. All right, and here's power available, okay? And with power available, it's the same thing. This is power required, this is power available at that speed, and wherever you have the biggest overage, wherever you have the biggest difference between what I need to maintain altitude at this speed and what I have is going to give you your best rate of climb over time. Okay? So there's your power and rate, best angle, best rate of climb. Okay, let's see, anything over there that, no, okay. All right, let's talk about absolute and service ceiling real quick. So here's absolute and service ceiling. So every airplane is going to have these two limitations on them, an absolute ceiling, a service ceiling, and an absolute ceiling. So typically we talk about the service ceiling. The service ceiling is the altitude to which we can climb to whereby our rate of climb decreases to at or below 100 feet per minute. Okay? So when we take off out of here, for those of you that are paying attention to the rate of climb indicator, if you take off out of here at VY and you start climbing, what kind of rate of climb are you getting? Anybody ever pay attention to that here? What kind of rate of climbs are we getting on an average day? How much? 500. Yeah, 500, 600 feet per minute, something like that, 500 feet per minute, okay. The higher you go, what happens to that rate of climb? It starts decreasing. We start getting a lower and lower and lower rate of climb. Well, the reason for that, let me show you the reason for that here. Let me just back up to this chart right here. This curve right here, this power required curve doesn't change, okay? But this power available curve does change. So this power, anytime you see these power, this power curve right here, this is a sea level plot. This is a sea level plot. What happens to this power available as we go up in altitude is this. So let's say that's 1,000 feet, 1,000 feet, 1,000 feet. We get to a point where our climb rate is anemic. Okay, so at sea level, we got a good climb rate, but then we go up a couple thousand feet and we don't have as much, and less, and less, and less, and less. And we'd get to a point where if we got to right there, where we could no longer climb, we would be at the absolute ceiling. We have no more power over and above what's necessary just to hold altitude right there. We cannot go any higher. We have no more excess power. There's none left in the bank. So as we climb, the excess power decreases and decreases and decreases and decreases. So if we get a 500 foot per minute climb rate right here, the higher we go, the climb rate decreases, all the way to zero. You see that? See how that would happen? Okay. So this power available from the propeller, what's the propeller doing? How's it creating this power? Well, the engine's turning that propeller, but then that propeller is giving us that power, right? It's atmospherically determined. So the higher we are in the atmosphere, the less power is available both to the engine and the power that's coming from, well, in this case, the engine and propeller combination. Okay.
Obviously, it has something to do with power and the power of the engine and the propeller as well.
So the propeller side is really more the thrust, but this is showing you just the engine side. This is really just the engine side.
But regardless, those two things and how they vary is what's going to determine the maximum climb of any kind of.
Well, this is your climb rate, yes, and that is your angle of climb. So this is propeller thrust. The other one is engine power. Okay. Your thrust is also, this is also doing the same thing as we climb. It's doing the same thing. Okay. It's dropping off. Okay. Let's go back to, where were we? Right here. All right, so when we reach an altitude where our climb rate diminishes down to 100 feet per minute, we have reached the service ceiling of the airplane. If we continue to climb to where we just can't climb anymore, we have reached the absolute ceiling of the airplane. Okay? And these limitations on the airplane are really engine dependent and design dependent, but engine dependent, right? So this is typical of maybe you could get some normally aspirated engines to get up to 20,000 feet, but typically when you talk about general aviation piston engines, normally aspirated, you're looking at 14 to 16,000 foot service and absolute ceilings, somewhere in that neighborhood. If it's normally aspirated, if you turbocharge it, supercharge it, now you can get up higher because now the engine can develop more power. You can get up higher. Okay? So look at the speeds here. if you look at the speeds here, you see that this is your Vx and this is your Vy. And what happens to your speeds as you climb? They change. And they're going to come together at the absolute ceiling. They'll come together at the absolute ceiling. Okay. This is a little bit not correct, but this should actually do this. And this should do that. But that's okay. And this would do this because, well, I don't know, it'd be too much to get into. I would lose everybody if I went there, so I'm not going to get into that. The important thing you want to recognize is that your Vx and your Vx and Vy are not shown on the airspeed indicator, are they? This is why they're not shown on the airspeed indicator, because they change. At least the Vx does. They change with altitude. Oh, one other thing. This particular airplane, let's say that its service ceiling is 17,000 feet. It's shown at 17,000 feet. What altitude is this? Is this 17,000 feet true altitude, absolute altitude, pressure altitude, or density altitude?
It's true.
Density altitude. It's density altitude. It's, yeah, I mean, this is where, okay, so it's 17,000 feet on a standard day, or it's when the atmospheric conditions are at a 17,000 foot condition. And that's all the power and thrust I'm getting out of this guy. Okay? So if you're flying an airplane that has a 15,000 foot service ceiling, that doesn't necessarily mean you're going to read 15,000 feet on your altimeter when you stop climbing or when you get to within 100 foot, right? It means when you get to a density altitude of that, that's where this is going to occur. Because everything about aircraft performance depends on density of the air, density altitude. All right. Talk about the region of reverse command here. So region of reverse command. So this is that power available and power required curve that gave us our VY numbers. How many of you have gotten into past level 2 in your training? Okay, so you're all familiar with this region of reverse command. So this is where we do slow flight. This is slow flight back here. So what this is saying, if you look at this power required curve right here, you see that whatever this speed is, whatever that V speed is, if I want to fly faster than that V speed, what do I have to do with power? I have to increase it. Power starts, as I go faster, power begins to increase. Okay, so so this is where we're normally flying. We're flying over here in the front side of the power curve most of the time. Most of the time we're over here, okay? And so this is a place that we're familiar with. And so let's talk about this for a second. So if we're flying out here on the front side of the power curve, we're at this speed out here somewhere. And I say, okay, let's maintain altitude and let's slow the airplane down. What two things do we have to do? First of all, what one thing, let me back up. I want you to slow down. Forget altitude for a minute. I want you to slow down. What do you have to do? What controls airspeed? No, what controls airspeed? How do we control angle of attack? Pitch. Okay, so if I want you to slow down, what are you going to do? You're going to increase the angle of attack. And we're going to slow down. Okay, so along this entire speed line here, if I want to slow down, now just look at the speed side here. Here's what I'm going to do. Slower, 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 slower. Faster, 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 faster. So the angle of attack must increase. To fly slower, you must increase the angle of attack. Okay? But now let's look at the power side of things. Something happens here with power. Over here, if I want to slow down, I increase the angle of attack. But if I don't do anything with power, just simply increasing the angle of attack is going to cause a climb. Because I have more, when I do this and I start slowing down, I didn't change the power and I have more power than is necessary and I start climbing. So I have to get rid of that excess power by decreasing power if I want to maintain altitude. So slow down and decrease power, decrease power, decrease power, decrease power, decrease power. But as soon as I get to here, now angle of attack more to slow down, but start increasing power, increase power, increase power, increase power. That's the region of reverse command because you're doing things backwards. Back here, if I want to fly slower, it takes more power. If I want to fly faster, it takes less power. More power, less power. Over here, they kind of go together. More power, less power. I want to fly faster, I increase power, but I decrease the angle of attack. Does that make sense? So this is the region of reverse command. Sometimes we call it being behind the power curve. All right. We do things back here. What's one of the things that, and this is a dangerous place to be. This is a dangerous place to be in certain flight conditions. And we've talked about one of them today where I didn't specifically say this is where we were, but what one thing that I talk about from a performance standpoint that puts us back here? What kind of takeoff? VX. VX is back here. You're back here in this region of reverse command in VX. It's a dangerous place to be. You're also back here when we're doing short field landings. You're back here in this VX, in this region of reverse command. So it's kind of a dangerous place to be. All right, let's take a break. It's 10 o'clock. If you didn't sign in, please sign in for me. All right. Okay, we'll get going again. Let's talk about landing, or takeoff and landing performance. So takeoff distances specifically, not so much climb performance. So a couple of things factors that affect takeoff and landing performance. These are, I mean, probably quite obvious, but maybe you don't think about them unless you kind of verbalize them. But runway surface, paved versus grass. You got a paved runway. Your takeoff distance is going to be shorter, and your landing distance is going to be longer. If you have a grass runway, your takeoff distance is going to be longer, and your landing distance is going to be shorter, right? Make sense? The runway gradient, do we have an upslope or downslope runway? That's going to affect both takeoff and landing distance for obvious reasons. You can understand that. You take off with a downslope, you're going to get off the runway quicker because you've got gravity helping build up the speed a little bit. If you land with a downslope, you're going to need a longer runway for the same reason, and the opposite then is true. Where would we find specifically these two things, runway surface and runway gradient? Where would we find that information? Do I have one? Somebody have one with you? The book, the green book? Yeah. All right, anyway, it's the airport facility directory. The airport facility guide or airport facility directory. It's the green book. We refer to it as the green book. In that, you can find every public use airport. If it's a private airport on the sectional, you won't get the information. But if it's a public airport, you can go to the airport facility directory, and it's going to tell you about the runways, the surface of the runway, what it is, what the gradients are, and all that kind of stuff. All right, water on a runway can affect performance. Okay, hydroplaning is something that you want to worry about. So there's a formula for hydroplaning. It's 9 times the square root of the tire pressure. So 9 times the square root of the tire pressure will give you the speed at which you need to be at or below in order that you don't hydroplane. So tire pressure on these planes is 30 PSI. So somebody tell me what, if we got water on the runway, what speed do we need to be conscious of? Huh?
5 times 5 is 25, which is closer to 30, so 5 times
49.
49? Okay.
Miles per hour or knots?
That's, it's going to be miles per hour.
Okay.
Yeah. Miles per hour, yeah. All right, so 49. So 50. All right. So should we be landing faster than 50? There's no circumstance I can think of at any time that we'd be landing that airplane going faster than 50. Right? Shouldn't be. You shouldn't be landing faster than 50. 50 is your flaps up stall speed. You'll be landing with flaps down. Your flaps down stall speed is 45. Then you're in ground effect. So, I mean, you're not watching the airspeed indicator, but when the airplane hits the runway, you should be doing something more like 40 when you hit the runway. Okay. So, what's that? Yeah, 49, yep. Okay, wind, obviously wind is going to affect takeoff performance. Wind in the face, shorter takeoff, shorter landing distance. Tailwind, longer takeoff, longer landing distance. This is obviously why we land and take off into the wind. Well, it's not only from a landing distance standpoint, it's also our ground speed standpoint, right? So our ground speed is slower when we hit the runway, or when we leave the runway, whichever way, whether we're taking off or landing, our ground speed is slower. Therefore, if something got squirrely and we had an incident or accident during that phase of flight, we want to be going as slow as possible. Okay, and then pressure and atmospheric conditions, in other words, density altitude. So density altitude affects everything.
Question,
Yes.
being that we're in ground effect on landing.
Yeah.
Stall speed, the SOP.
Yeah.
Does it tend to get a little bit lower being that we have greater lift as we enter ground effect?
No, we don't have greater lift. Ground effect is not more lift. What is ground effect? It's less drag. Ground effect is less drag. We lose induced drag, or we lose a portion of induced drag because the ground affects it.
Does it not also give you a little bit of extra lift when you're ground effect?
No, it's a, so what is induced drag?
These drag effects kind of like that.
So what causes induced drag?
Down.
The downwash that's created because of the production of lift. So when we generate lift, we generate induced drag. So if we get rid of induced drag, then the aircraft performance is better because we've reduced that drag. And what is, if you had to visualize induced drag, what does it look like? What's it look like? If you had to visualize induced drag, what's it look like? It's these vortices coming off of the wing, right? So what's causing the vortice? Pressure differential. You've got low pressure. Hey guys. You've got low pressure on top. You've got high pressure on bottom. Okay? So you've got high pressure trying to come here, and suddenly there's no wingtip, right? Or there's no wing, and so the air comes up like this. The airplane flies through it, and you end up with this vortex, this spiraling vortex. Okay?
It's also known as wake turbulence. Right?
That's also wake turbulence. So wake turbulence is, wingtip vortice is induced drag. So that's your induced drag. And its largest, when is induced drag going to be at its biggest amount? When is wingtip vortice going to be the largest it's going to be, its biggest quantity? When you're slow and heavy. Slow and heavy. And dirty, right? Or draggy. So basically landing is when you're going to have takeoff is when you're going to have the majority of it, because you're heavier on takeoff than on landing, but it's landing and takeoff. They're going to induce it. And the reason is, think about the pressure differential here. And when I'm flying in cruise, so remember, how much, if this airplane weighs, let's say this airplane weighed 10,000 pounds. How much lift do I have to generate? 10,000 pounds. If I'm flying like this at 200 knots, am I generating 10,000 pounds? If I'm flying like this at 100 knots, am I generating 10,000 pounds? All right? So my lift isn't changing. What is changing is this right here. This is changing. This is the angle of attack. This is the coefficient of lift. The bigger that angle of attack, the bigger the difference in pressure. So let's say my pressure difference, say I'm just going to make up some numbers here. Let's say that I'm pushing down here at 11. No, I'm pushing down here at 10, and I'm pushing up here at 11. I have a net 1 force up, right? And so as that net 1 force comes up over where there's no wing, I get a little corkscrew turbulence right here as the plane flies through it. What if I'm flying like this? Now let's say I have a net down of 10, but I have a net up of 20. Now I have a force down of 10, force up of 20, I have a net of 10. Now it's a much bigger force, which gives me a much bigger turbulent wake. So it's not about how much lift I'm generating, it's how much pressure differential I'm generating, which is giving me the lift that I need. Does that make sense? That's why when you fly slower, the lift isn't changing. The amount of lift is the same. What's changing is the pressure differential in order to generate that amount of lift. And when you have that giant pressure differential, you get a big, giant, turbulent wake when the wing stops right here. Okay. And because of that big, giant, turbulent wake, when you get into ground effect, so here we've got our plane flying, and you've got the wake, you know, coming off of the wing, doing this, right? But as soon as we get close to the ground, it affects it. It reduces it, or it eliminates it the closer we are to the ground. Okay, so what is drag? Drag is this retarding turbulent flow coming off the back of an object we're trying to move through the air. That's what drag is. It's the air, it's the flow of air, the air trying to get around this thing, and it creates this turbulent wake behind it. That's drag. This is the turbulent wake behind the wingtip, or off of the wingtip. And if you can stop that turbulent wake by hitting the ground, well, then you've stopped that induced drag. If we're up in the air, that induced drag just keeps on. This whole thing is pulling us back. It's a retarding force. The closer we get to the ground, the more we eliminate that force. So when we get into ground effect, how do we get on this subject? When we get into ground effect, that turbulent flow goes away. Oh, we were talking about landing distance here. And we're able to fly at a slower airspeed because we have a reduction of drag, not because we have an increase in lift. We have a net increase, I guess you could say, in lift, but it's because of reduction of drag that's causing it. Okay. All right, let's look at different types of airspeeds. These are performance speeds that we see on the airspeed indicator that we work with. All right, so let's talk through these. VSO, velocity, stall, in the landing configuration. So this is stall speed, stall in the landing configuration. Okay. Is this shown on the airspeed indicator? What's that? Okay, so yes, it is shown on the airspeed indicator, and it is the bottom of the white arc or white range on the airspeed indicator. It's the bottom of the white range on the airspeed indicator. So that's stall speed. So in our planes, then that would be flaps down. So landing configuration means flaps are down, gear is out, slats are out, whatever, from a configuration standpoint, whatever you do to the airplane to get ready for landing, you're configured that way. And in that configuration, what will the airplane stall at in a 1G condition? What will it stall at? Our planes is what? What's the number? 45 indicated. 45 indicated, okay? Okay. Will it fly slower than 45? When? We were just talking about it.
Grounds.
In ground effect. It'll fly slower than 45 in ground effect. But if you're not in ground effect, it's going to stall at 45. It won't fly slower than that. Okay, VS1 is stall in the takeoff configuration, or clean, I'm just going to say clean configuration. This one, sometimes I'll call this one dirty. Dirty, this one clean. So dirty, when we say clean and dirty, we're talking about drag, the drag from a drag standpoint. If you have a lot of stuff out, the gear's out, the flaps are down, you got your hand sticking out the window or something like that, you're dirty from a drag standpoint. If you're clean from a drag standpoint, the gear is up, the flaps are up, you're as clean aerodynamically as you can get. So that would be the stall speed. Actually, VS1 means stall in some specific configuration, really is what VS1 means. In our case, on our airplanes, the only configurations we have are flaps down or flaps up. So this is flaps down, flaps up for our airplanes. You could have airplanes that have VS1 or VS2 and VS1, VS2. They are still referring to stall speeds, but in specific configuration. So VS1 might be stall speed with flaps down, but the gear is sucked up. VS2 might be flaps down, gear down. VS3 could be some other configuration. So when you get VS with some number next to it, you have to know what configuration is that for that specific airplane. Okay. All right. VY, what's VY? And oh, is this on the airspeed indicator, by the way?
Partially starting.
Bottom of green. Bottom of green, yep. Okay, VY, what's VY? We've been talking about that. Rate of climb. So this is best rate of climb. All right, is that on the airspeed indicator? Why not? It changes why? Changes with density. Yep. So it's not on the airspeed indicator, no. Okay, VX.
That is,
Best angle of climb. Okay, is that on the airspeed indicator? Why? Changes because of density. Okay. VLE, what do you think that one is? Landing gear extended. Okay, landing gear extended. That means landing gear is completely extended. Okay. VLO.
landing gear, I guess landing gear, what's
VLO. It's landing gear something. Operating or operate in operation. It's moving. Or operational. Okay. These are typically not on the airspeed indicator. They're typically placarded by the landing gear lever. You'll typically see a placard right by the landing gear lever or knob that gives you VLO and VLE. So you know what speeds you got to be at to get them moving and what speeds it needs to be at before they're completely down. Okay? VFE. Flaps extended. Flaps extended, and here I'm going to put full extension. Is this on the airspeed indicator? Where's it at? Top of the white. Does everyone know what I mean when I'm talking about specifically you? Do you know what I mean by these color codings when I'm writing this? Okay, let me show you over here real quick. Since you're sitting right next to the picture. Here's the airspeed indicator. See these colors? Okay, that's so top, bottom of the white, top of the white, bottom of the green, top of the green. It's airspeed ranges, and we color code the airspeed indicator. That's what those mean.
Thank you.
Uh-huh. All right, VA. VA. Maneuvering speed. And what is maneuvering? Well, first of all, is it on the airspeed indicator? No, it's not. Why not? Who said that? It's weight dependent. All right. Which way does it move? As we get heavier, does the speed go up or does the speed go down? Speed goes down, speed goes up,
Oh,
speed goes up.
Heavier, the easier it is.
What's that?
Heavier, the less load on the wings, because the angle of attack is higher.
So does the speed go up or speed go down? If I'm heavier, VA goes up or VA goes down? VA goes up. So I got an up, an up, an up, a down. Oh, now an up, an up. Okay, it's up. Yeah, it goes up. So it goes with it. The heavier the airplane, the faster the VA. The slower the airplane, or excuse me, the lighter the airplane, the slower the VA. It moves with speed. Where would you get those numbers from?
You're operating in.
The operating, the handbook, the operating handbook. That's where you get them from. VNO, normal operating. VNO, normal operating. And is that on the airspeed indicator? Yeah. Top of the green. And then VNE, never exceed. And that is,
Do we also put that line right there?
no, that was just my cursor when I
see.
screenshotted that. Yeah. So this is the red line. So it's just a red line. It's not a range on the airspeed indicator. Okay, so that's typical. Other multi-engines will have different things. They'll have blue lines. They'll have single engine speeds and stuff like that. But for what we're flying, this is typically what you'll have on your airspeed indicator. Now, with electronic flight displays, the VX and the VY might be shown. They might be shown because these electronic displays with their air data computers can compute density altitudes and then put VX and VY numbers on the airspeed tape for you. And a lot of them do. Okay, a lot of them will do that. But an analog airspeed indicator is not going to have it on there. A digital one, flat screen, might have VX and VY shown on there because you'd have to calculate it with the density of the air. Okay, that makes sense? All right, any questions on that stuff? Okay, you want to do some performance stuff? Why not? All right, now you need to get those folders out that I gave you, and we're going to go through and actually do some performance calculations. Show you how to do them. And what you're going to find, if we have time, I'll pull up the Remos stuff. For those of you that have looked at the Remos charts, performance chart, their whole handbook is pretty lax. There's not a lot in the handbook. Okay, so what I use are Piper and Cessna charts. So that's what we're going to look at. And we'll start with a takeoff. So what we'll do is we'll go through. We'll do a takeoff distance. We'll do a climb. Time, distance, and fuel burn to your climb. We'll do some cruise stuff, landing stuff, all that kind of stuff. Kind of go in the order of actual flight. All right. So what you'll see when you're looking at this. Let me see this just real quick. All right. So when you open this up. You got a couple of tabs right in the beginning there. And the first tab behind those charts that we looked at, the first set of charts that you see are going to be graph format like that. They look like this. Those are going to be Piper type charts. And then the next tab are going to be table type. Turn to the graph. They'll be table type that look like that. And those are the Cessna type charts. All right, so different manufacturers will give you their performance information maybe in a table like this, or it might be graphical like that. We're going to do both so that you kind of see how to do it. All right, so the first thing I'm going to do is the first one I have up here is the This is a short field takeoff for, this is a Cessna, so find this. You should have this under the Cessna charts. Find this particular chart. Short field takeoff distance. It's figure 5.5. You have it there?
15-4 page. 14, sorry. 14
Oh, 5-14 is the page. Everybody have that? Does everybody have access to, do you guys have one?
We don't have one. Yeah,
Yeah, we're gonna need to, who can spare one? There we go. Okay, so the first thing I want to say about these types of charts, and Cessna typically has these, this is their typical format. Piper's format is the graphical type format. And I like one over the other, and I think after you go through this exercise, you're going to like one over the other as well, probably for the same reasons that I like one over the other, but we're going to use both of them to show you. I'm not going to tell you which one my favorite is yet. Okay, when you get this kind of chart, you need to do one thing and be very careful and diligent about doing this. Read every note on that chart. You need to understand the notes on that chart and what it's telling you, okay? So we'll get into doing that. But let's look at the chart here real quick. And you see two things. We're doing performance. What two things have to be included in this chart for it to be a performance chart? Pressure, altitude, and temperature. You have to have these two things. And you'll see these two things in every performance chart that you have. Because by getting pressure and temperature, it's calculating density, altitude, and how is the aircraft going to perform at these densities, okay? All right, so Cessna, and I think this is a 172, lays out, sea level up through 8,000 feet, and 0 Celsius up to 40 Celsius, and which we'll do here today. We'll do a few of these. If your particular circumstance doesn't fit exactly at one of these pressure altitudes or exactly one of these temperatures, we have to do something called interpolation, and we have to figure out what the numbers are in between are and figure out what the answer would be. That would be interpolating, all right? And there's a lot of interpolation that you would do with respect to performance calculations. There may be times when you want to interpolate, okay? You never want to extrapolate, okay? Extrapolating would be saying, okay, I'm at 9,000 feet and 50 degrees Celsius. So when you extrapolate, you're coming outside of the data set. When you interpolate, you're working inside of the data set, okay? So if you had to extrapolate, then you want to do it with great care and put a large margin of error in your answer. When you interpolate, you can do that with much more accuracy. Does that make sense to everybody? Okay. All right. So let's just look at this chart. First of all, this is a short field takeoff. So that means that you're going to use short field technique, and in this for the Cessna 172, you would go to the normal procedure section and look at a short field takeoff procedure. But it's essentially going to tell you need your flaps at 10 degrees. You're going to go full throttle. You're going to hold the brakes, go full throttle before you release brakes. This is assuming a paved, level, dry runway. If it's not paved, level, or dry, you have to do something down here. You have to increase or decrease or do something down here. It's assuming zero wind. If it's not zero wind, you have to do something down here, okay? And then it's saying, okay, we're going to lift off at 51 knots indicated, and we're going to, and then so that's our VX. And then once we've cleared our obstacle, we're going to pitch over to VY. This is what this is saying here. So you would find this information in the short field takeoff techniques laid out in section 4, which is normal operating procedures. Does that all make sense? All right. Let's look at the notes. Number one, short field technique as specified in section 4. So you're going to go to section 4, you're going to look at the short field techniques, and this is how we perform a short field takeoff in this airplane. So if you don't perform the takeoff as it says to do it in section 4, then this isn't what you're going to get. All right? Second, prior to takeoff from fields above 3,000 feet elevation, the mixture should be leaned to give maximum RPM in the full throttle static run-up. What does that mean? Why do we have a mixture control in an airplane? In some airplanes?
Because the air is thinner.
Because the air is thinner, right. So as we go up in altitude, the air gets thinner, but the volume of air is less, but the volume of fuel doesn't change. So what do we have to do? We have to lean the fuel. We have to say, okay, I got less fuel, we got less air, therefore I can't deliver as much fuel. I got to lean the fuel. I can't mix as much fuel with it.
Pretty sure we did that in either 2 weeks ago or last week. We just
We-
talked about yeah.
Yes, we have talked about it. So this shouldn't be new. If you've been through these classes, this isn't a new concept. All right, so if you're above, this is generally the accepted thing that you do with piston engines that have mixture control when you're above 3,000 feet. 3,000 foot, what? 3,000 if you're at if you're at an airport that's at 3,000 feet, you do this? When do you do this?
Above.
When the density altitude is 3,000 feet, you do this. So you might be doing this here, right? So remember, everything about an airplane, everything about the way it performs has to do with the thickness, the density of the air. It does not matter what your true altitude is above sea level. The airplane could care less how high you really are above sea level. All the airplane cares about is how far apart are those molecules spread out in the air right now. That's all it cares about. So you have to be thinking about that as well. All right, so how do we lean the mixture for best power? We hold the brakes and we run the throttle all the way up. And we look at the RPM if it's a fixed pitch propeller. If it's not fixed pitch, we look at manifold pressure. We look at the power, whatever our power indicator is. It's either going to be RPM if it's a piston engine, RPMs or manifold pressure. Power all the way up. Whatever it is, it is. Then we start leaning. And as we lean, what do you think is going to happen to the power? It's going to go up. We're going to get more power, more power, more power, more power, more power, more power. And then all of a sudden, we keep leaning, it's going to be less power, less power. And we push it back, more power. Wherever that peak amount of power is, we stop leaning. That's what we want to take off with right there. We are leaned for best power right there. That make sense? Okay, that's how you get best power before you take off. Then you're going to decrease distance 10% for each 9 knots of headwind. For operation with tailwinds, up to 10 knots, increase distance by 10% for each 2 knots of tailwind. So look at there, that's not a one-to-one relationship. So, and it's important to recognize, this is why we land with headwinds. A 5-knot tailwind is way, way worse than a 5-knot headwind. They do not mean the same thing. Okay, so you get 10% for every 9 knots of headwind. You get a reduction of 10% in takeoff roll for every 9 knots of headwind. You get an increase of 10% for every 2 knots of tailwind. Big difference. Okay? All right, for operations on dry grass runway, increase distance by 15% of the ground roll figure. All right, and then where the distance value has been deleted, climb performance is minimal. So over here. So basically, if you're at 8,000 feet, 40 degrees, I would just stay on the ground.
I don't think that
In
would
this
ever
airplane.
happen.
I would stay on the ground. I'd wait till early in the morning when you don't have this condition. When you can start moving these this way. Okay? All right. So let's do one. Let's assume. So everybody get your notes out, and you can look up here. You can do it on your book there. But we'll make something up. Let's say we are at. We'll make it easy. Let's say we're at 4,000 foot. We have a pressure. Get something that writes fairly well here. We have a pressure altitude. We'll call it 4,000 feet. Okay. We'll say the temperature The temperature is 20 degrees Celsius. Let's say we have a 10 knot headwind and we're on grass. Okay. So let's calculate two things, or let's find two things. Let's find how much runway do we need before the wheels leave the ground, and how much total distance do we need to clear a 50-foot obstacle. Okay, so two things we're looking for. We want the runway length, and we want the distance, total distance, to clear a 50-foot obstacle. Okay, see if you can figure that out. If anybody's stuck right off the bat, just raise your hand. Everybody, where are you stuck at? You don't have a book using that one? Okay. All right, so there's two columns. We need to look at two columns here. We need to look at pressure, altitude, 4,000 feet. And we need to look at temperature, 20 degrees. So here's 4,000 feet right here. Here's 20 degrees right here. So when we follow and when we find the intersection of these, we've got these two numbers right here. Okay, so that's where we're starting. Those are the numbers we're starting with. So we have a ground roll being the runway length. So maybe I should put ground roll there, but that didn't confuse anybody, did it, when I said runway length? Ground roll and runway length, same thing? Do you have a question? I thought somebody had their hand up back there. Okay, and then the total distance to clear the 50-foot obstacle would be 2630. So if these are the conditions and I didn't have a headwind and I wasn't on grass, if I didn't say, hey, here's a couple of conditions that aren't accounted for in these numbers, then the answer would be, the runway length would be 1,435 feet and then 2,630 to clear the obstacle. So here's what this looks like. Here's our runway. Here's our obstacle over here, our 50-foot obstacle. What this is saying is that I take off from here and I go 1,435 feet. And then the airplane takes off and I'm able to clear that obstacle in a total of 2,630 feet. That's what those two numbers mean. Does that make sense? So this is my ground roll. So under these conditions, if I take this out, if I take the headwind and the grass out of it, if I don't have to do anything with these notes down here, and my pressure altitude is 4,000 and my temperature is 20, the answer would have been 1,435 feet, and then total to clear the obstacle, 2,630. Does that make sense? Okay, now I can derive another number out of this. What other number can I derive out of this? I can derive this distance, and I could call this the air distance. It's not shown in the chart, but I can do simple math, right? Well, so what's 2630 minus 1435?
Uh, 1195.
1195. Okay, so there's three sets of numbers that I've got, and I haven't done anything with this yet. And that's fine. So now let's apply these adjusting factors to that, okay? So what's the first thing I said? I got 10 knots of headwind. All right. What does the note say about headwind? Decrease distance 10% for each 9 knots of headwind. Well, let's just call that 10. Okay. So we get 10% off of it. And so are we going to get 10% off of this only or the total? Off the total. All right. So you got 2630 times 10% equals 263 feet, right? So I'm going to subtract 263 feet, but I'm not done yet. Now we got grass. What do we do with grass? Where is it at?
Percent, number 4.
Number 4. For upper on grass, increase distance by 15% of the ground roll figure only, right? Because we're only in the grass for here. So we're going to take that number. We're going to take 1435 times how much? 15%? Is that what it was? 15? Times 15%, what is that?
397.
And we're going to add 397 feet to that. So we're going to take the total of 2630. We're going to subtract 263 and add 397, and what do we have? And that's our answer, whatever that is. Somebody do that. 2722? Is that what it is? I believe you. 2722. So it's going to take us 2,722 feet to clear the obstacle. Huh?
Is that what it's saying, not gonna happen?
No, I'm just saying you need 2,722. As long as you've got that much distance, you can do it.
For some reason, my calculator is not something.
Does everyone understand how that? This was a real simple one, okay? But you need to look at this when it's a chart like this. They're going to give you here's a standard set of data. This is a standard data set, and here are adjustments you would make to the standard data set. Now, in this case, we didn't have to do any interpolation. We just had, because I gave you a 4,000 foot pressure altitude, and I gave you a 20 degrees Celsius. But if I had said 3,500 feet and 15 degrees, now we'd have to interpolate between some sets of numbers. And we're going to do some of those. I'm not going to do them yet, though. I want to show you. I'm going to come back and we're going to do some interpolation, but I'm not going to do it yet. All right. Then we took our headwind, and our headwind's going to affect everything. The headwind affects everything. All right, so that was a decrease of 10% off the total distance that it gave us, right? And then an increase on the ground. Actually, you know what? I did this wrong. What did I do wrong here? I'm just thinking of this. I did something wrong here.
You used the wrong number,
Yeah, you used the wrong number.
What did I use?
1435.
No, ground is 1435. That's correct. What's wrong with this number? I'm just now recognizing that I made a mistake here. What did I do wrong? Think about the order of when I made these corrections. Think about the order of the corrections to the overall problem.
Don't you have?
What'd you say, Neil?
Except to remember.
Well,
Cumulative, so basically you have to do the 1 and then you have to add 50%.
I need to add the 15% to this before I take the 10% off for the total. You see what? Okay, so this number here shouldn't be 2630. What I should have done is that 1435 times the 15% is 397. Okay, so really what I have is 397 plus 1195 is what?
That'd be wrong for the thing, I give you a bad answer.
1532.
1532. So
1592. 1592.
actually here 1435. I'm getting everybody confused now. That's 12. That'd be 13. That'd be 8. So 1832. This would actually be 18. Is that it, right? 1832. Hold on. All right, everybody stop. I don't want to confuse everybody too much. Let's start this over. What I recognize, let me just start this over and show you what I did wrong here. Let me show you what I did wrong here. This is my standard, right? This is my standard. Okay. So I have two corrections I'm going to make to it. I'm going to make a headwind correction. So my headwind correction is going to subtract 10%, right? Off the total. 10% off the total. Okay? But my total is not 2630. Because this has to go up by 15% before I have the total because I have grass. So what is this number? I got to change this first. This number is actually not 1435. It's 1435 times 15%, which is what? 1435 times 15% is what? 215 feet?
Are you sure it's times?
Or not times, added to it. 1435 times 15% is what? Then add that to the 1650? All right, 1650. So my total distance that I'm taking 10% off of is 1650 plus 1195.
So you're saying that it's additive before applying subtractive and not in the order of notes.
You forget the order of notes. Yeah, the order of notes doesn't mean anything. You got to use some common sense, which I didn't do initially, because I'm on grass. Therefore, my distance, I have to take into account my grass distance, and then I can decrease that by 10%. So we're going to come up with a different answer here. If I take 1650 plus 1195, what do I have?
2,845.
How much?
2,845.
2,845. To that, we subtract 10%, which would be 285 feet. Minus 2845 leaves what? What's the answer? 2845 minus 285 is what? 2560. That's the answer. What did we come up with the first time?
2722.
Right.
I even said so.
Right. Okay, does that make sense? Everyone kind of wrapping their head around this? All right. You think this is my favorite type of chart?
But that's what I was questioning earlier, does that mean you can take off? Do you have enough space to get over that?
Well, you have to know. Well, now you have to say, all right. Well, what do I have? So I need. So in this case, in this scenario, okay, I need 2,560 feet from where I start to where this obstacle is.
Right.
If I don't have 2,560 feet,
You make-
I might hit it. So something's got to change, right? Now, when you look at these types of charts, these Cessna charts, typically they are at that weight. What weight do you think that is? That's max gross weight. Well, what if you only weigh 2,000 pounds? These numbers are going to get better, but by how much? I don't know, because they don't give you any way to calculate it. Okay?
But you can use that as a calculation to get a rough idea. If I can make it with gross weight, heavy gross weight, I can make it better with lighter weight.
That's the reason these are done at gross weight, because if you're under gross weight, all of your numbers. This is a worst case scenario.
Hey, remind me again, gross weight includes fuel or that's just?
Gross weight is just the gross weight of the gross weight is the maximum weight the airplane can weigh to legally fly it. Empty weights, you're thinking of empty weight.
Empty.
Yeah, empty weight's the weight of the airplane without usable fuel, without payload. Okay.
Yeah.
Just for everyone's knowledge, that they ask these darn questions.
They absolutely ask. You absolutely get these questions. You're going to get questions on your written where you're going to have charts that look like this, or charts like I'm getting ready to show you, and you're going to have to calculate this stuff using these charts. You're absolutely going to get a couple of these, I promise you. Okay, so you need to know how to do these calculations. All right, now let me talk practical for a minute. Practically speaking, go up. So let's say that we actually had 3,500 foot pressure altitude, and we had 15 degrees Celsius. I could interpolate, or I could simply use these numbers. I could go to the worst case, and if the worst case works, I'm just going to go with it. Does that make sense? Okay.
if you're doing that on your own.
If it's from a practical,
You're
I'm
doing it
talking
on a
practical. If you're taking the test, you better interpolate and come up with the right answer. Does that make sense? In the real world, use the worst case. Go to the next column. Go to the next pressure altitude, go to the next temperature, and if it's going to work there, then you know, then you should be okay. Okay, all right? All right. Let's do another one. Let's go to the Piper chart now and do a takeoff problem on the Piper chart. So go to, it's figure 5.9. I don't know what, it's this one. I don't know what page it's on there, but it should be one of the first ones under the Piper tab. Once you find that, let me know what page that is for everyone. Should be the first. 515. Let's see. Figure 5.9, yeah. Okay. All right, here's how Piper does it. I like this chart better. You're going to quickly understand why. Look at how many, this is an example. Okay, this is the little sample that they have here, the dotted lines. So don't worry about that right now. But look at the notes. If you take this out of it, look at the notes of where you have to apply correction factors. How many notes on here that apply correction factors are there?
Just that section? I'm not seeing it.
None.
Flaps, takeoff, ground.
Well, this is just the conditions.
Well, that's figure 5.11.
Yeah, 5.9. Go to figure 5.9.
So 5, you got 5.7.
Oh, 5.7. I'm sorry, 5.7. Why did I? 5.7. 5.14. Sorry about that. 5.7. I apologize. Okay. So what do you have? You take that out, you have no notes. You have, basically, you say the associated conditions are paved, level, dry runway, full power before brake release, flaps are 0 in this case. Okay? All right. Let's assume we have we'll just do the same thing. We'll say we have a pressure altitude. I said 4,000 feet before, right? Pressure altitude of 4,000 feet. And I said temperature of, what did I use? 40 degrees Celsius?
Yeah.
40 degrees Celsius. All right.
So 20.
Oh, 20 degrees Celsius? Okay, 20 degrees Celsius. Sorry. I mean, it doesn't matter. It's a different airplane, but I just want to use the same numbers that I used. You could use whatever. Okay, now, let's say that we are at a gross weight. In this case, we're going to say gross weight. So for this airplane, gross weight equals 2,400 pounds. And I'll show you how I know that on this chart. And then we had a headwind of, what, 10 knots?
Yep.
10 knots. Okay. All right. Now this one doesn't give us a means to do anything with grass. There's no means on here to do anything with grass. I don't see any notes on here for grass. Okay. All right. So we're going to assume we're on a paved runway here. Let me just show you how to use the chart. And then I'll show you how to factor grass in from a practical standpoint. All right, so we're 20 degrees Celsius. So here's my 20 degrees right here. And if I go straight up that 20 degrees Celsius line, I'm just going to draw it straight up, straight up, straight up, straight up, straight up, straight up. There's my 20 degrees Celsius line. Here's my pressure altitudes. When I go to 4,000 feet, here's the 4,000 foot pressure altitude right there. So I've just accounted for pressure and temperature right there. So I've got density altitude accounted for right by doing that. I came in at 20 degrees at a pressure altitude of 4,000 feet. You have a question?
Oh, no, I was just
Okay. So there are essentially three charts in this chart. Here's a chart here, here's a chart here, and here's a chart here. And we're going to move from chart to chart to chart and then come up with an answer over here. Okay? So we start here. Now we've got that answer. We move horizontally right out to the next chart, which starts at this reference line right here. So we come to right there. Now we're entering the next chart. The next chart is the weight chart. So Piper doesn't restrict you to the gross weight. It lets you do things if you're under gross weight. In this case, I said we're at gross weight, which happens to be the reference line at 2,400. So that would be it right there. I'll show you, let's say we were at only 2,200 pounds instead. We would then, you see these reference lines curving like this? You'll kind of want to follow those lines down, all right? In this case to 2,200 pounds. So here's 22 right there. And what I want to do is kind of follow these lines down in this direction, kind of sort of right about there. 22. Now I'm done with that chart. And I come horizontally out of it into the next chart. Right over to reference line right there. Now I got winds. Now I deal with winds. I've either got headwinds or tailwinds. And look at the slope of the lines. Look at the slope of the headwind versus the slope of the tailwind. Which one has a greater gradient? The tailwind. Yeah, so tailwinds hurt, okay? So I said 10 knot headwind. So here's my 10 knots, right in, I don't know, right in here somewhere, right at that line right there. And so now I'm going to follow these reference lines this way to right around here. And there's my answer right there. Just under 1,500 feet. That is my ground roll. That's this right here. That's the ground roll. This chart's only giving me ground roll. I got to go to another chart for my air distance. So now if you go to, the next chart is the same chart but with 25 degrees of flaps. Yeah.
Next one is the 0
Yeah.
takeoff performance.
Yeah, so this one here is 25 degrees flap. So then you go to the next one. What chart do I want here? I can't.
The one's 5-9.
5-9. Yeah, here you go. So here's takeoff performance. So now you would go to this chart. 0 flaps, because that's what we did on the takeoff, on the ground roll. So now you can get your takeoff performance, okay? So if all you care about is total distance to clear your obstacle, and you don't care about the ground roll portion, you can just go to this chart. If you need to know the ground roll portion, you go to the other chart, right? So using the same thing, 4,000 pounds at 20 degrees Celsius, we're going to come in, 4,000 PA, pressure altitude. Here's 4,000 right here. Okay, and then we come over to the reference line, and then down to 2,000 right here, and then over to here, and then up to 10 degrees right there. Total distance is 2,400 feet to clear the 50-foot obstacle.
That's quite easy.
It's quite easier, isn't it? You just got to make sure you stay in kind of on the lines.
Now,
Okay.
your ground roll is included in that?
Ground roll's included in this. So that's why I was saying if you're not worried too much about getting off the runway, you don't need to know how much runway distance you need. You just need to know total distance to clear the obstacle. You go to this chart. If you need the runway distance, you use the other chart. So you have to be careful which chart you're using. Does that make sense?
In other words, let's say you have X amount of runway that's kind of short.
Okay.
But your obstacle's further beyond that.
Did you want to do both
You
of them?
want to do both.
You want to do both. If you actually have a short field, you want to do your takeoff roll, and then do this one as well, and then the difference between those two will give you your air distance. Okay, then got that? All right. Let's move to this guy here. So let's go back to your Cessna charts. Now we're going to do fuel. Time, fuel, and distance to climb. So we're on figure 5-7. Okay, so we've taken off. We've used the chart to get off the ground and to clear the obstacle. And now we want to say, okay, what's our climb performance going to be like? Getting up to where we got to go. Okay. How many of you are in or past cross-country phase? Okay, so one of the things that we calculate is top of climb. This is where you get top of climb. If you have this type of chart in your particular handbook, which we don't in the REMO, so we have to calculate it differently. But if you have one of these charts, you would use this to get your top of climb. And you're going to get a bunch of information. You're going to get the time it takes you to get there. You're going to get the fuel it takes you to get there. And you're going to get the distance downrange you're going to be when you get there. So you get those three things. So if we're taking off, we take off here and we're trying to get to here. Okay, that's our top of climb. All right, what we're going to get is the time it takes us, the distance it takes us, and how much fuel we burn getting there. That's what the time, fuel time and distance to climb is, all right? So let's say we're going to, we're going to climb to a pressure altitude of 5,000 feet. Okay? Here's our pressure altitude. Here's our temperature. And, well, first of all, let's read the notes, first of all. So you're going to add 1.1 gallons of fuel for engine start, taxi, and takeoff allowance. So that needs to come into this fuel used column right there. You're going to add whatever you end up with here, you're going to add 1.1 to it to get the right answer, especially on a test. Your mixture is going to be leaned above 3,000 feet, just like we talked about before. You're going to increase time, fuel, and distance by 10% for each 10 degrees Celsius above standard temperature. So notice that the temperatures right here are standard. What should the temperature be at 10,000 feet? It should be -5 degrees. What's the temperature at sea level? It's 15 degrees, right? So these are standard 2-degree lapse rates. So if you're non-standard, you have to account for it over here. You're going to have to do some interpolation and account, or not interpolation, but accounting for it based on that. And then, excuse me, the distances shown are based on no wind. So you would have to figure out what your distance would be downrange based on wind. You'd have to factor that in using the backside of your E6B. All right, so let's say we got standard conditions. We're at 5,000 feet, standard temperature 5 degrees, and we're climbing at our indicated airspeed of 75 in this case. Those are our numbers right there. Those would be our numbers. Rate of climb would be about 500, would average out to 515 feet per minute by the time we got there. Notice how the rate of climb at sea level is 720, right? 170 once we get up to 12,000 feet. See how that rate of climb changes, okay? Our time in minutes, it should take us 8 minutes to get there. We're going to use 1.8 plus 1.1 for our taxi and doing whatever we did. And our distance downrange would be 11 miles. So this is how you would use, you would get your top of climb on your navigation log, right? On your nav log to get to your top of climb right here before, you start your cruise phase. To get here, these are your numbers, okay? So now let's assume we're taking off from an altitude of 2,000 feet. These numbers now are going to change, right? Because these are based on starting at sea level. What if we start from 2,000 feet? Well, if we start from 2,000 feet, then that means that these would be our numbers to get to 2,000 feet, so we'd have to subtract those. You understand? So let's assume this is 0, this is sea level, but we're starting from here. We're already 2,000 feet up. So to get from sea level to 5,000 feet, it's going to take us 8 minutes. But to get from sea level to 2,000 feet, it's going to take us 3 minutes. So we're starting from here, so it's only going to take us 5 minutes.
So you basically.
Did I lose everybody?
That could also be density altitude.
These are all density altitude. All of these everything is density altitude. That's why you always have to go back to your density. You have to go back to actual pressure, altitude, and actual temperature if you want to correctly calculate these things. When you're talking performance numbers, sea level altitudes mean absolutely nothing. Everything is pressure. All right, so in this case, our time in minutes would actually be 5 minutes. Our fuel used would be 1.1 plus the 1.1 would be 2.2. And our distance would be 7. Does that make sense? Right? Because we're not starting, unless you happen to be starting at sea level, then everything works. So whenever you use a time, fuel, and distance to climb chart, unless you're starting at sea level, you have to do two. You have to look at 2 sets of numbers and then subtract. Okay, because the chart's based on from sea level to some altitude. Okay. All right, and then. Oh, you know what? We didn't take a second break. You want to take a second break real quick? Let's take a second break real quick. Sorry about that. All right, let's do a time, speed, a fuel, time, and distance to climb on the Piper type chart. This is figure 519. So go to figure 519 in the Piper type charts. And we'll go over that. So it's the same concept, right? This is going to start from sea level, and then it's going to take you up to whatever altitude it is you want to cruise at. So it's going to get you up to your top of climb. But the same thing holds true. If you're not starting off at sea level, you have to do it twice and then take the difference between the two numbers. All right. So here's your fuel. So you're going to, it's typical of a Piper style chart. You're going to come in at your temperature, go up to a pressure altitude, and then you move horizontally to the next chart. Once you get into the next chart, you're simply going to just move straight through it. But as you pass through the fuel in gallons line and the time in minutes and the distance, you hit those and go straight down for your values. Okay? This can be a little hard to read when you get down over here. It's kind of hard to see what you're looking at. So you have to be careful with these. But let's say we're at I don't know, 20 degrees Celsius, let's say, and we're going up to, I don't know, whatever that is, 6,000 foot pressure altitude. Once here, then you're just going to come straight across through all those lines. All right. When you hit here, this one, this is fuel in gallons used. You would drop straight down to whatever that is. That's about what, 4 gallons? Something like that. Come over here to time, drop straight down. That's about 15 minutes or 16 minutes. Distance, 22 miles. See how that works? Okay, so that's your Piper style. Now, if you started at something other than sea level, let's say you started at 3,000 feet, you got to do the same thing. You got to go at 3,000 feet. Then you got to take these numbers, whatever these are, and subtract them from the others to get the actual numbers. In the interest of time, I'm not going to do that, but do you understand how it's the same thing that we did before? You have to have 2 sets of numbers, and you're going to subtract them to figure out where you're, based on where you're starting at. Okay? That's your time, speed, distance to get to top of climb. That's how that works on the Piper charts. This one probably has some notes. It's this one. Now this one doesn't have a weight thing in it, so it's calculated, in this case, at gross weight. It's telling you to lean your mixture per the Lycoming instructions, and it's a no-wind scenario. No wind scenario. Okay? All right. Let's look at cruise performance. Let's look at cruise performance chart from a Cessna standpoint. So this is figure 5.8. And so these, make sure we're reading the notes. Okay, we're at gross weight, as they typically will do. Cruise speeds are shown for an airplane equipped with speed fairings. Without speed fairings, decreased speed shown by 2 knots. Okay. Again, you have your pressure altitude column here and your pressure, altitude, and then temperatures. So this is for cruise speed. And your cruise speed and your fuel burn are going to be dependent on, in level flight, are going to be dependent on your power setting and your altitude, essentially, right? So what pressure altitude am I at? So let's say we're at 4,000 foot pressure altitude, as an example. Well, we could fly at, and let's say it's standard temperature. We'll go to standard temperature just so you understand how to read it. 4,000 feet, standard temperature. So this is the range of data that we're working with. Man, I need to get, one of these days I'll get pens that actually have ink in them. There we go. Here's our range of data that we're working with. All right, so whether we want to fly at a brake horsepower, we want a true airspeed of 117, if we want that, we're going to be burning 9 gallons per hour, and we have a horsepower of about 80% horsepower, 80% brake horsepower. All right, but we can drop our fuel burn quite substantially down to 5.8 gallons per hour if we don't mind losing a whole bunch of speed. All right, and our horsepower is back down to 50%. So we have some range of stuff that we want to work with, that we have to work with there. Do we want to get there fast and burn a lot of fuel, or do we want to burn less fuel and take a little longer to get there at less horsepower? Okay. Even so, regardless of where you set your horsepower, let's say we keep our horsepower at around 80%. So here's 80% at 2,000 feet, 80% at 4,000, 80% at 6,000, 80% at 8,000. We can't even get 80% at 10,000. We can't get 80%. The best we can get at 12,000 is 70%. Why is that? Huh? It's a normally aspirated engine. We don't have a supercharger or turbocharger. The air's thinned out. We can't even get that much horsepower, right? All right, so let's just look at these four. If we're at 2,000 feet and 80% horsepower, what's our true airspeed? 115. If we're at 4,000 feet, look at our true airspeed. If we're at 6,000 feet, look what happens to our true airspeed. 8,000 feet, look what happens to our true airspeed. It goes up. So the higher we go, the faster our true airspeed goes. Now, does that mean this is what we're seeing on our airspeed indicator? So if I'm at 8,000 feet at 80% horsepower, am I going to be seeing 122 on my airspeed indicator? Nope, I'm not. I'm not. I'm going to see indicated airspeed, not true airspeed. So it's this right here, right? This is my indicated airspeed right here. Density of the air times the true airspeed velocity. So as I go up, the density goes down, the true airspeed goes up. This remains the same. As I start descending back to sea level or back to land, pressure goes up, true airspeed goes down. What I see on the airspeed indicator doesn't change. Okay?
Question.
Yeah.
For example, on the 4,000 setting.
Here?
Right.
Okay.
And if we want to do, cruise at our best fuel economy,
Okay, down here?
that would be 5.8.
5.8,
That
yeah.
also gives us now an RPM of 1,900,
Right?
which is rather low on, for example, these planes.
Yeah.
Is that a concern?
No.
Should not be a concern.
Uh-uh.
Not for cooling, but I know it's cooler up at 4,000 feet.
No, that's not a concern. You're burning less fuel when you're down there. What's that?
If anything, it's the best, the opposite. Best performance, best situation. And that's,
Yeah.
That's prop RPM.
Yeah, this is RPM. Yeah, but in this case, this is a fixed pitch propeller. So it's giving you RPM, not manifold pressure. If this were a constant speed propeller, an airplane equipped with a constant speed propeller, then you could see RPM, but you'd also see an MP column. You'd see a manifold pressure column, because that would then be your power output. In the case of a fixed pitch propeller, RPM is your power indicator. So yeah, you're flying at lower power, burning less fuel, and what would happen to your range?
Significantly increased.
It would increase significantly. Absolutely right. That's absolutely right. If you want best range on an airplane, you're going to be flying around at VX or close to VX. You're going to be flying really slow.
Yeah, it's gonna take you a while.
It's going to take you a long time to get there, but you're going to burn. You ain't going to burn much fuel, but you'll go. Your range is going to be quite extended.
Yeah.
Yeah. Okay. All right, and then let's look at one of these for a Piper. So here's the way it looks on the Piper chart. So this is figure 521. So once you do a couple of Piper charts, once you do all of them, they're easy. They're all set up the same way. You're always coming in on these at temperature up to pressure altitude, then you move into another chart, move horizontally into another chart. And when you get into the other chart, now you can start looking at different power settings. Okay, do I want to go at 55% power, 65% power, 75% power, full throttle? And what power setting do I want? And then that'll give me my true airspeeds based on the power setting. Make sense? You want me to run through one of these, or can you visualize it after having gone through so many of them? Okay. Okay. All right.
This basically, this is your own determination as to what you want to accomplish.
Yeah, yeah, sure. What do you want to do?
You want to get there fast.
You want to get there fast, but then you have to understand. Okay, well,
What are you gonna lose from it?
if I want to get there fast, well, you have to really think about it. Let's say you want to fly from here to, I don't know, California or something. All right, and you can get there in one fuel tank if you fly at 70. You might have to stop 3 times or 2 times if you want to do 120. So how much time are you going to lose every time you stop to get fuel? Are you actually going to get there quicker?
Right.
It's gonna bounce back out.
Right. You got to bring that all into account when you're calculating it. You got to think about all that kind of stuff. Right? Okay. All right. Any questions on this stuff so far? All right. Let's see if let's do a couple of let's see if I have it up here. Okay, let's do some of these. Oops, it's not showing up. Why isn't it showing up? There we go. All right, let's do a couple of these. I've been trying to do some of these sample tests as we get to the end of the classes each week. All right, so what is ground effect?
Well, I checked it.
Yep, looks like A. Has to do with the airflow patterns, all right? All right. What's the effect of a temperature decrease and a pressure altitude increase on the density altitude from 90 degrees Fahrenheit at 1,250 feet pressure altitude to 55 degrees and 1750 pressure altitude. All right, let's see if we can find this figure. Why don't I have it up there already? Let's go look here, grab it. Okay, what figure was it? Figure 8. Figure 8, okay. Oop. All right, so the question was effect of a temperature decrease and pressure altitude increase on the density altitude from 9. So we got 90 degrees Fahrenheit. Pressure altitude increase in density altitude. 9 degrees Fahrenheit and 1,200 feet, 1,250 foot pressure altitude to 55 degrees Fahrenheit and 1,750 pressure altitude. Okay, so we got 90 degrees Fahrenheit, 1,250 foot pressure altitude. 90 degrees Fahrenheit, right here. 1,250 pressure altitude is going to be somewhere in here. All right, and the question was, what was the question? Was the effect of temperature decrease? Okay, I see.
Top center.
Yeah. All right, so here we have a, what are our answers? That'll tell me what I'm looking for.
I'm pretty sure 1,700 foot increase, 1,700.
Okay, yeah, we're looking for the pressure out, we're looking for the density altitude change. All right, so this one is getting us, if I'm doing my line right, just under 4,000 feet. And then 55 degrees Fahrenheit to 1,750. 55 here up to 1,750 might be here somewhere. So what is that? 1,700 feet-ish, something like that. Does that seem about right? Decrease. So how about that one right there? Does that make sense? Okay. All right. What effect does high density altitude have on on aircraft performance? What effect? A, B, or C? A. Oh, why did I skip that? I hit the wrong. It was A. I had the thing in the wrong place. All right. Ground effect is most likely to result in which problem? Which problem will ground effect manifest? B? Everybody good with B? Okay. Refer to figure 8. It's the one we were on. What is the effect of temperature increase from 30 to 50 on the density altitude if the pressure altitude remains at 3,000 feet? So 30 to 50 with a, so 30 to 50 with a PA of 3,000 feet. And the question is, what is the effect on temperature? What is the effect? Oh, what is the effect of temperature? But it's still pressure altitude. Okay, so PA of 3,000 feet, but we're going from 30 to 50. All right, so 30 degrees. Up to 3,000, right there. 30 degrees and 50 degrees.
26,000.
Oh, I'm looking over here. Sorry about that. 3,000 right here and 50 degrees right here. So we have about 1,500 feet or so. So probably this one. Okay. Floating caused by the phenomena of ground effect will be most realized during an approach to land when at, yeah, A, less than the length of the wingspan. All right, so let me explain what that means. So if you take the wingspan of the airplane, okay, here's the ground. If you're within this distance, so here's the ground. If you're within this distance, you have some ground effect occurring. Very little, but some. And the closer you get to the ground, the more and more and more and more and more and more you get. So as long as you're within this distance, there is some ground effect occurring. Okay. What effect, if any, does high humidity have on aircraft performance? Increases? Decreases, okay.
Because humidity actually pushes their air molecules farther apart.
There you go, see? All right, how will frost on the wings of an airplane affect takeoff performance?
A.
Okay, make sure you read all the questions first. It is A, but don't jump right to the first thing that looks right, okay? Read them all. It is A in this case.
Yeah, I was wondering about gotchas.
Yeah, they will give you gotchas like that. So they'll ask, there will be questions. This is a good example of one. There'll be a question like this, and the first thing, frost will disrupt, and you see that, boom, that's the answer. But then if you keep reading, it might totally blow that out the window.
Yeah,
And
it
so
might disrupt
just
the
make sure
force.
you're reading all of the answers to make sure it
I
fits.
saw the references to Fahrenheit, by the way. I'm under the impression a lot of the test questions are in Celsius, or does that not?
They'll go both ways. They'll have Celsius and or Fahrenheit, but there will always be a key. Yeah,
Like you did on
Yeah,
that other example?
yep.
Okay.
yeah. You don't have to know the formula you don't have to mathematically calculate back and forth. There'll be a key there.
Okay.
All right, which combination of atmospheric conditions will reduce aircraft takeoff and climb performance?
C?
C, yep.
It's funny because we all had the same realization at the same time.
Okay, we figure 8, so that's the same one. What is the effect of temperature increase from 25 to 50 on the density altitude of the pressure out? I'm not going to do that. We've done 3 of those already. I'm going to move to the next one. We all know how to do that, Kite. All right, after takeoff, which airspeed would the pilot use to gain the most altitude in a given period of time? All right, and when we're using VY, is that giving us, is VY excess power or excess thrust?
Excess power.
Excess power, it's a rate function, excess power, VY. Okay, what must a pilot be aware of as a result of ground effect?
C.
C, yeah, it's an induced drag issue, lack of. Okay, there you go. All right, we got all right, we have 7 minutes left over. So in that 7 minutes, I'm just going to explain this because I got a question on it anyway. So I'll just explain what this is. So I said earlier that whoa, oops,
Oh, really? Was that the laptop?
that was my Surface Pro. Yep.
Oh.
Thank you. All right. So I said earlier that making funny noises. That's not good. There we go. All right. I said earlier that that as we go up in altitude, Vx and Vy, or at least the diagram showed that Vx and Vy do this to the point where they come together. All right. And then I also said I'll just redraw that. I also said that what they demonstrated wasn't exactly correct, so I'm going to show you why that is. So if this is my speed, okay, and this is your power side. So if the power required curve looks like this, right, and the power available curve looks like this, the point where I'm gonna back this up over here a little bit so it makes more sense. The point where you have the biggest difference between power required and power available, that is Vy, right? Because you have that excess power we talked about, okay? What the chart in the book shows is Vx is over here, Vy is over here, and they come together at the absolute ceiling. They do come together, but Vy doesn't really change, Vx does. And that's what I'm gonna show you why. So this is a sea level plot, remember, right? So the amount of power that's being shown right there is the power I can develop at sea level with high density air. As I go up, I can't develop as much power. But the power that's required to maintain altitude at that speed, these are indicated air speeds. That's this speed. That's this speed. Okay? It's what we see on our airspeed indicator. So it doesn't change. Even though the density changes, the speed indicated doesn't change. Vx you would use the other chart to calculate, but you can also get it off of this chart by drawing a line from the origin to the tangent right there and dropping straight down, and that is Vx. Okay, that's another way to get Vx. So what happens as we go up in altitude? The power required to maintain the speed and level flight doesn't change. The indicated airspeed doesn't change. Our true airspeed's changing, but our indicated airspeed's not changing. But the power the engine has decreases. As I go up, my power curve does that. My difference, my maximum excess power is still at this speed line, but Vx now changed. Vx would end up, over here somewhere. So Vx starts encroaching onto Vy. And the higher I go, I'll get to a point where there's my power curve. There's Vx. So the higher I go, the faster Vx becomes until it catches Vy. So that's why in the book it shows Vx, Vx doing that and Vy doing that, and they do come together, but it does this. So that's what I was explaining to Daniel. All right. Questions on performance? What's the most important thing that you need to understand about performance, aircraft performance? What's the most important factor? Density altitude. As density altitude increases, what happens to performance? Goes that way. Except for one metric. There's one metric that goes up. There's one performance number that gets better. Huh? No. True airspeed. Your true airspeed goes up. This is your true airspeed right here. This is indicated airspeed. This is true airspeed. As the pressure decreases, we go up in altitude. As the pressure comes down, the true airspeed goes up. But that's also why we need more runway. Because to take off, even though we're still indicating the same thing, our true airspeed is actually faster, and we need more runway to build up to that true airspeed to get off the ground, even though it's indicating the same thing. We need more runway now to take off. We need more runway now to land, because even though our indicator airspeed doesn't change, we approach at 70, right? We approach at 70. We approach at 70 whether we're at sea level. We approach at 70 if we're at 10,000 feet. Why? Because that's our speed. It doesn't change. Now, Our true airspeed is changing dramatically, or could change dramatically, but the indicated airspeed, the pressure that we're reading, that's not changing. That make sense? Okay. Yeah, so true airspeed is the only thing that I suppose gets better. And you said fuel, and fuel actually does, because here's why fuel does, because as you climb, you could actually throw that power setting back. You're losing a little speed, but you're also gaining speed because of the altitude gain, right? So you could pull the power back and maintain a speed that you would have at a lower altitude with a lower fuel burn. So yeah, you can burn less fuel up there. Okay. If you look back, open back to that chart, that very first chart in there. I'll show you something. If you look at look at this chart right here. Okay. And if you look at the last column, the very last column, it says true airspeed / indicated airspeed ratio. So that's basically saying what's the ratio of the true airspeed to the indicated airspeed, the true airspeed to the indicated airspeed. Okay. Look at sea level. If you're at sea level on a standard day, what's the ratio? 1. So if you're indicating 100, what's your true airspeed? 100. All right. Go to 10,000 feet. What's the ratio?
1.16374.
Okay, so if you're at 10,000 feet, pressure, altitude, and and temperature there. If you're indicating 100, what's your true airspeed? 116. Okay. All right. Go up to 40,000 feet, which is where your airliners fly, and they're up there flying at an indicated airspeed of 250. What's their true airspeed? 500. Why do you think they fly up there?
So they go faster.
Yeah, and they burn less fuel
Actually,
because they're in the
fun
thinner
fact,
air.
There's actually sometimes been records of planes going supersonic, actually. Because there's one time in A321 XLR, if I'm not wrong, was flying from somewhere to somewhere, I can't remember.
Yeah.
But its indicated airspeed on Flight Radar 24 was 821 knots.
That's pretty incredible. That's pretty fast. Pretty fast. All right. Questions?
The difference between like with the line having excess thrust and excess power, that threw me off a little bit. Can we look at that again?
So think about rate and angle. Okay. Rate is a time thing, right? What rate of speed are we flying? It's related to a clock. It's related to time. Power, 1 horsepower. What you say it was? It's the time. It's
How much can move 550 pounds a foot in a second?
it's how much power is required to move 550 pounds 1 foot in 1 second. So power is a rate function. So when you think best rate of climb, it's excess power because it's rate. Rate and power go together. And then the opposite would be Vx would be thrust. Is that what you're asking about? Yeah. And I've seen, and I believe there are questions on there, best rate of climb, you could get one. Best rate of climb is a function of excess thrust or excess power. Excess power. Because it's a rate thing. Power is rate. Power is not a force. Power is time. Power is time to move a weight a certain distance. Thrust is a force.
So weird. I've never thought about that.
Okay, well that's so when we have the 4 forces, it's not power and drag, it's thrust and drag. That's a force, thrust. Okay. Get something to eat.